Okay, so this is the third lecture in the monads series, and I'm going to spend it talking about applicative functors. So I want to start by going back to the parser that I wrote yesterday and critiquing it a little bit. So there it is, you remember it, I'm sure. But it's a little bit wordy, isn't it? Wouldn't it be nice, for example, in the definition of term, to replace that sequence of monadic parsers by a call to lift M3? And of course I can do that. I have to combine factor, exactly, star, and factor with a multiplication. So I can use lift M3 and a lambda expression that takes A, throws away the second argument, takes B, and then returns A times B. But it's a bit annoying that I have to ignore that second argument. If only lift M3 would do that for me, then I could simply pass the multiplication function here. So I could write something like this. Here's a version of lift M3 that takes the first and third arguments and throws away the second. Now I can just say lift M3 x underline x multiply factor exactly star factor. Yes? What is that second argument? So up here in the term definition, okay, let me just make sure that I can write on my slides. Yes? Is that exactly star? Okay, that's a monadic computation. It produces a value. It's actually just the star character. But I have to throw that away somewhere. There I am throwing it away. So I can do this, of course, but now I have to have a variant on lift M3. How many variants am I going to need? Well, 8, I suppose. 16 variants of lift M4. Oh, it's not nice, is it? So I can solve that problem by breaking lift M3 down into smaller parts. That's what we're going to be doing today. So let me introduce another operator. I'm not quite sure how to pronounce this. Maybe I'll just call it apply, although it's not. Which, for any monad, takes a computation that delivers a function and a computation that delivers an argument and just gives you a computation that delivers the result. So it kind of lifts function application. Dollar is the Haskell application operator up to the monadic level. And if I define this operator, which is, as you can see, it's easy to do, then I'm going to be able to rewrite lift M fx as return f star x. So f here is of type A to B. I have to turn it into a monadic computation with return so that I can then use star to apply that to x. So for lift M, that maybe doesn't look too sensible, but for lift M2, I can now do the same thing. I can just take a binary function f, lift it to the monadic level with return, and then use this monadic application to apply it to each argument. Lift M3 likewise. So this is rather nice. Now I only need to define this one star operator, and all of those k lift functions I can just construct on the fly. And by the way, of course, this operator has to associate to the left, just as function application does. So it's declared to do so. Okay. So if I do this, then I can also easily create variations on this apply operator that ignore one of the arguments. Why would you want to ignore an argument? Because you want it only for its effect, of course. So let's define two variations. This one discards the right argument, so you can see that it takes an MA and an MB and it returns the MA. That must be the left argument. And I can easily construct that now by using the const function in Haskell. It takes two arguments and returns the first. So if I just lift it to the monadic level and apply it this way, then it's going to give me the result of A. And I can define a corresponding operator that ignores the left argument instead. So you can see it takes the second one and returns it. Just by doing something similar, but here I need the function of two arguments that returns the second. And that I can construct as const ID. So now if I use these operations to combine monadic computations, all of the effects will still happen left to right, but some of the values will be discarded. Now, there are going to be a lot of operator names to remember here, so I want to give you a mnemonic for remembering what they mean. You can think of the less than and greater than as pointing towards the operands. So these operator names are chosen so that the less than and greater than point towards the arguments that are used. So if there's no less than or one-sided operator, it means that argument is discarded. Okay, so now if I go back to the expression parser, I can rewrite it like this. There we are. So look at the first line. To parse an expression, well, I'm going to apply the plus operation in the end. So let's use return plus. And then I apply that to what's parsed by a term. And then I throw away something parsed by exactly plus. And I apply my function that I'm building up to what's parsed by another occurrence of term. Or else, I just parse a term. And likewise, I can rewrite all of the parsers that I wrote yesterday in what I think is a much more attractive style. Okay, so this is more concise. That's good. And many people think that this kind of style of programming is more applicative in feel, more functional in feel. The same stuff is happening behind the scenes, but the previous notation reminds people of imperative programming, whereas this notation reminds people more of applicative programming. I don't know whether you feel that way or not, but at any rate, it's one potential advantage. Yeah?
A little bit on the one-sided ones. So the reason that they have a direction to point is that they're taking two different kinds of things. No, they're taking the same kinds of things, but they're throwing away one side.
Yes, they're taking an MA and an MB. Right, so they're the functions of two arguments. They're essentially the current versions of first and second. And the mnemonic I was trying to give you was that you need to remember which one is which. How do you remember which argument is being discarded? Well, there's no add less than or greater than point.
If you write a long expression involving these bracket star and variants, the first term in that expression will be a function, morally.
Exactly.
Applied to the results of all of the others.
The way I'm going to use it is that the first term in that sequence is always going to be return function. So I'm taking a constant function and I'm saying, okay, turn this into a monadic computation so that I can use these monadic operators to combine it with arguments in an analogous way to just applying a function to arguments.
So aren't you tempted to replace return plus bracket star by plus brackets dollar sign?
Not only tempted, but I will succumb. Just try not to introduce too many things on one side. So, before we do that, I want to make a more serious critique of the library that I showed you yesterday. And that is that backtracking is actually a rather inefficient way to parse most grammars. So here is the guts of the backtracking. It's the implementation of M plus for the state transformer, monad transformer. And you can see here that even if the first parse is going to succeed, all the time that that first parse is running, we don't know whether or not it's going to return nothing at the end of the day, or the empty list. So all the time that the first alternative is parsing, we have to keep everything required to parse the second alternative. What's going to be required? Well, that means we need to keep all of the input in memory, just in case we need to apply that second parser to it. We'll also need to keep the second parser in memory, even though perhaps it's not going to be used. So, in many grammars, we may know after parsing perhaps just one symbol on the left-hand side that we will never need to use the second parser, that it can never succeed. But this implementation doesn't take advantage of that, and so it's going to be very space inefficient. Okay. So how can we solve that? Well, what we would like to know is, in advance, that second parse is not going to succeed. So we can just throw it away as soon as we start parsing the first half. And one classic way to do that is to compute for each parser what tokens it can accept as the first token. So then we can look at the next token in the input, and before we start applying the first parser, we can ask, well, is there any possibility that the second one will accept this? If the answer is no, we can just throw it away. And indeed, if our grammar is LL1, then we're going to be able to choose precisely which parser we should use, just based on the first token. But we also need to know whether the parsers can match the empty string in order to apply this safely, because of course, if the second parser can match the empty string, then we're always going to be able to use it. So what we would like to do is to compute for each parser what its starter symbols are and whether or not it can match the empty string. Okay, and now, okay, as I was just explaining, if we come to an n+, then we can take advantage of this information to discard the second parser if we know we won't need it. So what I'm going to do today is I'm going to modify parsers so that a parser is a pair of the static information and the dynamic parsing function. And I'm going to take advantage of the static information to throw away parsing functions that I know I won't need. But there's a problem. And the problem is the implementation of the bind operator. Okay, so let's think about this. When I'm programming the collection of static information in bind, what am I going to have to do? Well, how do I know whether m bind f can match the empty string? It can match the empty string if m does and f does. How can I tell what the possible starter tokens are of m bind f? Well, clearly, any token that can start m can also start this combination. But if m matches the empty string, then any token that can start f can also start this combination. So how will I compute the starter symbols of m bind f? It's going to have to be the starters of m appended with the starters of f if m can match the empty string. But wait a minute, what am I talking about? What do I mean starters of f? F isn't a parser, it's a function. So I have to apply it to something. This question mark. What should I apply it to? The thing that m parses. But I don't have the thing that m parses yet, because I'm not going to start parsing m until after I know what the starter symbols of my parser are. Ah! So we're in a bind. And I'm sorry about that. Not very sorry, but yes. So we just can't do it. We can't define bind. And that's annoying because I'd really like to make this optimization. But wait a minute. Think back to the way that I rewrote my parser. I didn't actually use bind anymore, did I? I just used these new derived operators that I've just introduced. So suppose I want to know what are the possible starter symbols of f applied to m. Is that problematic? Well, no. because here's the first parser, here's the second. I can just take their static information, combine it how I like. So if I were to define this application operator directly, instead of in terms of bind, then I wouldn't have this problem. I have to give up on having a monad, of course, but maybe it'll be worth it. Since, after all, it seems that bind now isn't so essential for writing parsers. So this is the idea behind applicative functors, that we replace the monad interface by a different one that lets us do more stuff. This class definition at the top is the one that is in the libraries for applicative functors. So we have a type for the application operator that is just like the one I already showed you. We say that an applicative functor must also be a functor, and we need something corresponding to return, because I did use return, and we have to give it a different name. And so it's called pure. So pure converts an A to an FA. It's just another name for return in this case. So now I'd like to implement this interface, and I'm going to be able to implement it for every monad, at least. I can just define the application operator as I did before in terms of lift M2. So let me introduce a way of wrapping any monad so that I can write this applicative implementation just once. For any monad M, wrapped monad of M is going to be an applicative functor, and here is the instance. Pure A just wraps return, and the application operator is just defined using lift M2 as before. So having done that, if I want to use a monad as an applicative functor, I'll just use wrapped monad of M instead, and then I'll automatically have the implementations of these operations available. So what I've just shown you is that every monad is, or gives rise to, an applicative functor. But the reverse is not true. Of course, that's why we want the notion of an applicative functor. So for example, let me just consider determining whether or not a parser can match the empty string. I'll define a type empty of A that just is isomorphic to booleans. Okay, what's the point of this type parameter? It's there so that I can declare empty to be an applicative functor. So it has to have a type parameter for that. It's a phantom type, it's not used in the definition, but it has to be there. So now I can write an instance of this applicative class that just will tell me whether or not the corresponding parser matches the empty string. Does a pure parser match the empty string? Well, yes, it doesn't match anything else. It just leaves the state unchanged and just gives me a value. What about apply f to x? Does that match the empty string? Well, yes, provided both f and x can match the empty string. So I can just use Boolean AND here in the implementation for empty. So this is actually an instance of a very generally useful kind of applicative functor that does not correspond to a monad. It's just collecting information, and as long as we have some associative operator to use here and an identity to use here, in other words a monoid, then we can define an applicative functor in this way. Okay, so every monad is applicative. Not every applicative is a monad, but every applicative is a functor. And in fact, I'm always going to be able to define an fmap operation in terms of the operations in the applicative class. Fmap f of A is always pure f applied to A. So that's not a surprise. And unfortunately, I can't write a general instance like this, saying for every f that is applicative, let's implement fmap this way, because just as we discussed yesterday, the type checker would seize on this instance every time it needed a functor and say, great, let me simplify this constraint to this one. And that would not be a good idea. So sadly, when using this library, I actually have to write instances of this functor class by hand every time. I think I'm not going to show you those instances anymore because they're all syntactically identical and very boring. Okay, so applicative functors also give us a way of capturing some kinds of effects. But I just want to compare the expressiveness to the expressiveness of monads. And a very nice way to do that is to consider writing a conditional combinator. So you can imagine that I might like to write this function cond that takes a computation of a bool and then chooses between a then branch and an else branch. So both of those will have type MA, and the end result will be of type MA. Here's a monadic version. What do we do? Well, we write some monadic code that evaluates the Boolean and then selects the then or else branch as the next thing to evaluate. If we do that, then clearly the effects of this computation will depend on whether M gives us true or false. Evidently. When I write an applicative version of cond, I can do so, but I have to write it like this instead. I'm going to have to use the application operator to apply something to M, F, and G, and then I can, in the pure function, put my conditional that says, well, if B is true, take the then branch, otherwise take the else branch. So this should give me the same result as the monadic one, but the effects always evaluate M, evaluate F, and evaluate G. So this is more like a multiplexer in hardware, where you've got two circuits and they both run anyway and produce an input, and then you choose between the results. That it is like a conditional expression in a conventional programming language, which really determines the flow of control. And indeed, when you use applicative functors, the flow of control, as it were, the effects, cannot depend on the values that are generated. So all of the effects will happen anyway, but that's actually perfectly okay for a parsing library, at least if we're parsing a context-free grammar. I mean, our parsers don't parse the first part of the input and then use that to determine which grammar the rest of the input should depend on. Okay, if you wanted to parse, for example, operator declarations that specify a precedence, then you might indeed want to modify the grammar that the rest of the input is parsed with. In that case, an applicative functor is not your friend. But for at least the simple kind of parsers I'm going to talk about today, it's just great. So far, the advantage that I've shown you with applicative functors is that we get a nice notation. But actually, there are more advantages than that. Applicative functors are a lot more composable than monads are. So, for example, if I've got any two applicatives f and g, then prod fg is another applicative functor that just pairs together the values of the two functors. How can I convince you of that? By showing you the instance declaration, as usual. So how do I make a pure x? Well, I just make a pure x in each of the functors and pair them up. How do I apply prod fg to prod xy? Well, I just apply f to x and g to y and pair them up. It's very easy. You can do this with a monad too. You can take two monads, pair them together, and get another monad. But it's a bad idea. Why? Because it turns out that when you define the bind operator for this paired monad, you have to apply the f, the second argument, twice, once per monad. So if you write x bind f, you're going to have to call f twice. Well, now if you nest bind to the right, you can see you're going to incur an exponential cost. Exponentials are not good. So, in principle, you could do this with a monad. In practice, you can't. Yes?
What's that twiddle?
That twiddle is Haskell's notation for lazy pattern matching. So what does that mean? Well, normally, if you were to evaluate an application of this star operator, then we have to determine whether or not the arguments match the patterns. Now, you might say that the prod type only has one constructor, so obviously they match. Well, that's not really true, because the argument could be undefined. And in Haskell, bottom is different from prod bottom bottom. So we actually have to evaluate the argument and make sure that it's of the form prod something. We haven't seen this issue before, because with new type it doesn't arise. New type creates a new type that is actually isomorphic to the representation type. Data does not. So new type pattern matching is automatically lazy, you might say. Sometimes, though, I want to define a type like prod, and I want to pattern match on it lazily. What that means is that when I apply this clause, I will not evaluate the argument and check that it matches the pattern when making the application. I'll only do that when I use the bound variables x and y. So what that means is that I will be able to apply, to use this star operator to apply something to an as yet unevaluated argument, and it will not be evaluated just because I do that application. It'll only be evaluated when the values in it are actually used. And as we discussed yesterday, for those, for these recursive definitions, like my recursive parsers, it's essential that application is lazy. That twiddle is there to ensure that. That's a long answer to a short question, isn't it? And I'm sorry about that. This is a wrinkle. You just have to do it. Okay, so that was a product of two applicatives. We can also compose applicatives. So I can define another new type, compose fg, whose representation is just f of g of a. And indeed, compose fg is another applicative functor. How do I do that? Well, in order to make a pure x, I've got to make an f of g of a, so I just call pure twice. In order to compose them, I need to lift the apply operator with pure. So that's going to give me an apply operator that will work on the things inside the f. This is the pure for f, and this is the apply operator for g. And when I then apply that with the applicative application to f and x, then it will construct something of type f of g of a. If you don't believe me, type it into the type checker. So this is rather cool. And remember that every monad gives us an applicative functor. Monads in general can't be composed, but if we wrap them, then they can. That's a little mind-boggling, isn't it? There will be an example, but rather later. Okay, so we've seen that if I define a conditional operation using the applicative functor interface, it doesn't do what I want. It does all the effects anyway. So I would like to have a way of combining computations that does make a choice between the effects. And so let me define an analog of monad plus for applicative functors. So this is also in the applicative libraries. It's another class called alternative. So an applicative functor is an alternative functor if it implements an empty operation and a choice operation. And of course I can implement these for wrapped monads just by wrapping M0 and M+. So it's very simple to do. Okay, so now I'm going to be using this choice operation in my parsers, of course. Can I define my empty functor as an alternative? So what I need to do is answer the question, when does a choice between two parsers match the empty string? Empty is going to represent a parser that accepts no inputs whatsoever. Does that accept the empty string? No, it accepts no inputs whatsoever. So the correct value there is false. If I have a choice between two parsers, f and g, then how can I tell whether that will accept the empty string? Well, if either f accepts it or g accepts it, then the combination will. So now I can combine f and g with the Boolean OR operator.
So is this the one which accepts the empty string? Okay, but so it seems to me that you have some kind of recursion. Well, so you define this choice operator in terms of empty, and so the thing is, can you get empty true for?
Can I get empty true?
Yeah. So at what point do you match the empty string?
Here, this is the applicative instance for empty, and it says if you have a pure value, that matches the empty string. So here you can see that we're using and its unit, true. So we have one more node there.
Before you leave that slide, I was feeling confused about it before, and I think I still am. So what we're defining here, it says on the top line, can a parser match the empty string?
Yes.
Is there some other parser that we're thinking about here and telling whether it can match the empty string, or are we defining a parser that matches the empty string or doesn't, or something like that?
I might choose to represent parsers in a number of different ways. But I've got an API for building parsers, which I can use to build all of them. Now, you might think that the representation I choose ought to be usable for parsing. But no.
Right. So you're going to build a parser which is abstracted on not the monad but an applicative. And
yes.
You instantiate it on the empty applicative. You're going to find out whether it parses empty.
Exactly. So this is one possible representation of parsers that does very little. All you can do with it is find out, would it match the empty string? And of course, this is not the only representation I'm going to use, but it's going to be a parser to go to that more. Okay, where had I come to? We've done this. Yes, so in the applicative instance, I had true and. Here I have false and or. So it's kind of nice that way. Okay, so I can actually now continue and define some of the operations that we saw yesterday in a more general setting. So I showed you some and many. Actually, all I need to define those is the operations that alternative functors give me. So here we are. I can say sum f is, apply a pure cons operation to f and many f. Many f is either a sum f or a pure empty list. And these definitions will now be usable with every alternative functor, not just with my parsers. Down at the bottom there's another example. If I want to parse something optionally, I can say an optional f is either pure just applied to f, or it's a pure nothing. Okay, by now even I am getting bored of writing pure thing applied to something. So let me just introduce an operator that does that for me. This is the dollar enclosed in angle brackets operator, and it's simply equal to pure the first thing applied to the second. So it's just a derived operator, but it simplifies the syntax here a little bit. Once again, let me remind you that here we have recursion, And without lazy evaluation, this would not work. So that laziness that I talked about a few minutes ago is really vital. And actually, it's more efficient to define many and some like this. Here I've got a definition of some. You can write an analogous one for many. If you look at the original version I showed you, then you can see that some f calls many f, which then calls some f again. So we would end up with a recursion that makes many calls of some with the same argument. That's, in some cases, inefficient. So let me just replace it by a direct recursive definition. That some f is going to be a value s that is equal to cons applied to f applied to either s or a pure empty list. So making this change is actually quite important for the parsing application that I'm doing. Okay, so where have we got to? So if I now take the parser monad that I developed yesterday and I just wrap it, then I'll have an alternative functor that provides pure, this funny application, empty, alternatives, these alternative versions of application that just discard one of the arguments. We've just seen some and many. In other words, most of the API that I use for making my parsers is already generated by the library for alternative and applicative functors. So let me just wrap that in a new type and define a type of monadic parsers that just wraps up a state transformer on strings and derive the existing implementations for functor, applicative, and alternative. So this one line almost gives me my parsing library. What's missing? It's the exactly operation that I used previously. So